long-range purpose of unmanned exploration of the planets is the development of technology which will lead to eventual manned exploration. Scientifically, our objective is to assist in answering two basic questions. What, if any, life forms exist on the planets, and how has the solar system been formed?
I think one thing that must set apart JPL from other places is the willingness to take on challenges.
To be part of two great American institutions, Caltech with its legacy of academic excellence, and NASA, which gives us the foundation and the backing to reach for the stars, to look for answers. JPL has this tremendous tradition of being the first to do many things.
This legacy of firsts allows you to dream big. And you feel like you want to keep that track record going. You want to contribute to the next first.
It is far better to dare mighty things even though we might fail, than to stay in the twilight that knows neither victory nor defeat.
I don't know what can be more exciting than that. When you're creating the science, creating the knowledge, creating the technologies.
The quest is the culmination of all these efforts we're doing.
It's bigger than any one of us. It's a quest for all of us.
Among JPL's quest is quest to understand Earth's changing climate. The rate at which the climate is changing now is unprecedented.
We have a little bit of understanding. It's going to get warmer, sea levels are going to go up, but how much, where? What about my beach? What about my house? What about my yard? That's the stuff we don't know, and that's the stuff we desperately need to know.
In order to get that information, we have to fly payloads like radars, like radiometers, science instruments that can collect that data.
Water is important to all forms of life, including us as human beings on this planet. So understanding the water cycle is important to understanding what resources we have in different places, who's likely to be affected by drought, who's likely to be affected by floods, who's likely to be affected by storms, and understanding hazards around the planet.
JPL has really been a leader in understanding how the Earth deforms at the surface, whether it be volcanoes or earthquakes, using GPS receivers on the ground or using airborne or spaceborne radar platforms. We piece together a whole understanding of the system of earthquake faults, and it helps us understand how these things behave at depth and how they will behave in the future.
Mars is a great candidate for trying to answer this question about life in the universe by focusing in on places on Mars that could have supported life 3 billion years ago. That's the quest we have with Curiosity.
We've been following the water. We've been establishing habitability.
And then the third following question is there potential for there to be life today?
The Curiosity-like rover, Mars 2020, will go there with an increased challenge of finding signatures of past life, both as it drives around and in samples that it will put together in a collection that will one day be brought back to Earth.
But the human need is really to put one of us on the surface. It doesn't seem to satisfy us until we get footprints on a surface of another planet.
The plan with sending humans involves starting to land things even years before the humans would arrive. Pre-assembled structures or resources that could be set up, rovers that could start collecting liquid water in the form of melting ice or from these hydrated minerals.
We have the expertise here of getting to Mars and landing large structures there. Nobody else has done that. That will be the next challenge going forward, is landing something extremely heavy onto the surface safely.
When we go to another planet and we look at it with another set of instruments and we get a deeper look, we always come up with answers and we always come up with more questions. Juno is going to answer some of the things that are still unanswered since Galileo. And since Jupiter has the most mass of anything in our solar system outside the sun, that's going to tell us a lot more about the formation of the solar system.
If the planets got there in a specific way, and we have a model for that, that model has to reproduce even the configuration for the asteroid population. Because this is a primitive body of the solar system, we can understand about our solar system's origins. We take the observational data and we use this data to compute where these objects are, and more important, to compute where these objects are going to be in the future.
I'm building robots to explore these new places in the solar system that we've got our sights set on.
The asteroid retrieval mission advances JPL's quest to understand the nature and the origin of the solar system. The mission uses microspine gripper technology developed at JPL. ARM will capture a boulder roughly 6 meters in diameter from the surface of an asteroid and bring it to lunar orbit where astronauts can study it.
And as part of the mission, we're also going to try to do a gravity tractor. We're going to change the path of the asteroid. The reason why we're doing this is because we want to be able to protect the Earth from future impacts, and we want to develop the technology and test it out.
You get to go out and say, yeah, I'm going to save the world from the dinosaur-killing asteroid, and that's actually maybe a little bit true.
Of all the planets in our solar system, Venus is the closest to being a sister planet. It's our closest neighbor, it's the closest in size, and yet Venus is a very, very different place from Earth. Venus is basically what Earth would be in a runaway greenhouse.
We have a great opportunity now to send a mission there and really understand a lot more about how two planets that can be fairly similar in terms of size and distance from the sun, etc., can have such wildly different results.
Because of the incredible high temperatures and the high surface pressures on Venus, it may be one of the most difficult places in the solar system to reach. If there was any type of experience that would make the incredibly difficult merely possible, JPL would be the best place to really start exploring that. Everywhere we've looked on this planet, on Earth, where we see liquid water, we see evidence for life. And so one of JPL's quests is to look at the icy satellites of the outer planets. These are places where we see an icy surface and we see tantalizing evidence of liquid water beneath the surface.
The technology to search for life, to hopefully find life on a place like Europa exists, and we're sending it in an arsenal of instrumentation. We will be able to generate maps with really, really good resolution to be able to identify what minerals are on the surface, what phases of ice, whether organics are there, what kinds of organics are there. So this will give us a really unparalleled picture of Europa's surface.
Or to be able to get beneath that icy surface into the oceans and look for microbes or some other kind of organism would be just an amazing opportunity.
If life exists on Europa and it's leaving evidence of its existence, we will find it with this mission.
Discovering life that had a different origin than ours would tell us that the origin of life is a process as fundamental as volcanism or as fundamental as cloud formation, that whenever you have the environment for that to happen, it happens.
JPL's quest is to help answer one of the timeless questions certainly asked by the first Homo sapiens when they looked out onto the night sky. Namely, are we alone? And we now know that when you look up at the night sky, on average, every single one of those stars has at least one, if not multiple, planets. This is why it's this moment in time that is a real shift for us at JPL. Now the question is not are there planets, but is there life on these planets? And it's right now that the exoplanet program at JPL is starting to take us to the next step. Can we devise technology to enable NASA's missions to look for life on these exoplanets?
How much star formation happened? When? Where were these critical junctures that put a lot of energy from star formation into the universe?
I want to understand the constituents of the universe. That is, what is the universe made of? The universe is primarily dark energy, which is this mysterious substance that's causing the universe to expand faster and faster.
There's a lot of infrared information that you can get from supermassive black holes. Not the black holes themselves, but you can study them by what's going into them. and the supermassive black hole evolution seems to somehow quench star formation at a certain point in a galaxy. You put all these together, hopefully, we can get a better picture of how you get from something that's almost entirely smooth hydrogen gas to this very, very fragmented universe that we have today. We never are going to go to these other galaxies, but fundamentally, with all these new telescopes, we're there with our technology. I always wondered whether the people in the Renaissance knew they were living through the Renaissance, that this was a critical time. I know I'm living through the golden age of astronomy. The technology, particularly stuff being developed here at JPL, is making it possible for us to answer these questions.
JPL is known for exploring space, but I actually always love seeing the expressions on people's faces when I explain to them all the areas that we're touching their lives that they had no idea about. JPL's pioneering work in telecommunications and digital imaging and miniaturization are key components that make it possible for you to enjoy your smartphone every day. When you go to the doctors and they take your temperature, that's JPL inside of your ear. We pioneered a lot of that technology.
And because we're a federally funded research and development center, commercial companies or government agencies can come to JPL for any resource, whether it's building a satellite or helping the Department of Defense protect soldiers or helping find people buried in rubble after an earthquake. That's one of the things I'm most proud of about being at JPL is what we offer to the public.
There are a lot of purposes JPL has: to explore, to learn, to innovate. But the ultimate purpose, for me anyways, is to inspire.
Almost across the board, when you talk to the public, people are blown away by what we do here.
People are stunned and amazed when they see the stuff that goes on here firsthand.
And I think it's a privilege for us to engage with them and to share.
When you bring them on the journey, people feel like they're explorers themselves. They have the great excitement of the discovery, and they understand why you want to do this.
It really sort of reminds you of why you're doing what you do.
Everyone needs inspiration and hope. A lot of what I've seen JPL give to the world is that kind of sense.
You go talk to a group of school kids, it puts everything into perspective. It shows you what a privilege it is for us to get to work on these problems.
One of the things I love the most about JPL is that I'm working in a community of people who are inspired by what they are doing and feel that their work is really meaningful.
We are exploring space to the benefit of the species. That's a tremendous privilege.